Now let's consider how structural members and joints can be combined to create efficient structural systems. A structural system needs special combinations of joints and members to avoid problems. The 1989 Loma Prieta earthquake caused large enough displacements that a bridge fell off the support at one end. The same problem occurred in the San Fernando earthquake, when entire bridges fell off their supports. Supports are obviously important. Here's a beam that collapsed during bridge construction on Highway 29. If a rigid support had been used in place of a roller, the rotation and failure probably would not have occurred. Okay, let's look at how acceptable systems can be created.
The most basic structural system might be just a single span beam system on simple supports to hold it up. This bridge over the McCann River is just a large slab of concrete. The entire slab is like a beam spanning over the river. At the ends, the slab just sits on the abutment walls. A railroad crossing was needed over the Menai Strait in England with a long span. This double bridge was built to provide one track in each direction. The bridge was actually created with box girders. These are long hollow tubes with a rectangular cross-section. The trains run inside the tubes, and each tube is on a simple vertical support at each end. When we use the term simple support for a beam, we mean a pin at one end and a roller at the other. The pin provides a horizontal restraint, so the beam can't move sideways. The roller allows expansion or contraction. Both the pin and roller provide vertical support to hold the beam up. This Daytona Beach Bridge is a continuous beam structure. It is still simply supported, but it is continuous over more than one span. If the bridge were all single spans, we would see kinks over all the supports where the beams of the two spans rotate differently. When the beam is continuous, these kinks are eliminated. The rotation at the ends of the beam are also reduced, resulting in less sag and deflection. So now the beams are more efficient. The truss system has many more members than a beam, so it is more complex. All the members are pin-headed and are either in tension or compression, not in bending. So the internal forces are simpler. A critical condition for a truss is that all the members are joined to form triangles. If they formed a rectangle, the system is unstable, as evident in the popsicle stick model. If the diagonal is added to create two triangles, the truss becomes stable and acceptable. Braced frame systems used in buildings are like vertical trusses that cantilever up from a foundation. Here, however, the beams are pin-ended and have bending because they are loaded along their length rather than just at the joints. The diagonals in the frame resist lateral wind loads and provide stability. The columns work with the diagonals as a truss and develop additional axial loads. Braced frames are frequently used for industrial buildings where the diagonals are often tension rods or small angles. An unbraced simple frame relies on the columns acting as cantilevers fixed at their base to resist lateral loads. While the braced frame resisted lateral loads through truss action, creating axial forces in the columns, the unbraced simple frame uses bending in columns to resist lateral loads. This is less efficient, but preferred by architects for buildings where the diagonals of the braced frame would cross windows. This unbraced California frame was damaged in the Northridge earthquake. The cantilever columns were permanently bent sideways by the large earthquake forces. The simply supported beams were not damaged, however, but just moved sideways with the columns. Moment-resisting frames have rigid beam-to-column joints. The columns are generally cantilevered from fixed foundations. When the beams are loaded, they cannot rotate as much at their ends as they would if they were pin-ended. In order for the beam to rotate, the column must rotate as well. The rigid joints at the beam ends allow the columns to share in the beam load resistance. The beam will have smaller bending moments and less vertical deflection. Moment-resisting frames are more efficient than unbraced simple frames and can be used for taller buildings. They are also more effective for earthquake resistance, as in the frame in San Francisco, or the Petronas Towers in Indonesia. There are many other structural systems. Some are combinations of types we have looked at, like braced moment-resisting frames, as in Chicago's John Hancock Building.
This building in Vancouver is one of those unique structures. A concrete core, like a cantilevered box-shaped beam, is built up from the foundation to the full height of the building. Then, outrigger trusses are attached to the top of the core. Cables are suspended down from the truss ends. The floors are built at the ground level, then lifted up along the concrete core and attached to the cable when in the proper position. Looking from the outside, you can't tell that this is a suspended building, but it is odd that there's no column at the base.
Other structures, like unique shell structures, are much too complex for us to examine here.
In considering all the structural systems, we've seen that it's essential that a system must be able to resist both vertical and lateral loading. For horizontal systems like bridges, simply supported systems are often the most economical because of the simple joints and easy construction. On longer spans, however, continuous systems of beams or trusses are more efficient because controlling deflections becomes important. The restraint at joints of continuous spans reduce their deflections. Which system is best for buildings depends on the use of the building, the height, the material selected, and the loadings. Unbraced simple frames, often called pole buildings, may be the most economical system, but are limited to low buildings because the tall cantilevered columns bend too much under lateral loads. When used in taller buildings, the lateral deflections become unacceptably large. By adding cross braces to create a braced frame, the lateral deflections can be controlled with little extra cost. Braced frames are particularly suited for industrial buildings, where the cross braces don't have any architectural impact. They are very effective in reducing lateral displacement compared to an unbraced simple frame. Moment-resisting frames are a more expensive solution used in tall buildings. The cost of constructing the rigid joints between beams and columns is important. Still, they're often the most efficient system for taller buildings. Actually, combinations of these systems often really provide the best structural solutions.